So we talk about voltage leading current and things like that, time constants. Now here we're dealing with unit 14. So time constants, this is also known as the exponential curve. Read unit 14, it'll have a few explanations on that. But basically, we're talking about inductors and the time it takes to reach its full Ohm's law value. So when we talk about inductance now for Henrys, T equals L over R. And again, this is all sitting in that unit. So T, time in seconds, L is the inductance in Henrys, and R is the resistance of the coil. T, now time, is represented by tau. It's a Greek letter, I believe the 19th letter. And that represents one time constant. So when we do this calculation, T equals L over R, or the ratio of L to R, the T that we're calculating for right here is one time constant, represented by the symbol tau. So, for example, if a coil has an L of 1.5 henries, an inductance of 1.5 henries, a resistance of 6 ohms, the time required for one time constant is 0.25 seconds. So that's one time constant. So for the full Ohm's law value, I'm going to express it as F Ohm's law V, 0.25 seconds times 5 takes 1.25 seconds. So what you have here is the one time constant. This is what we're calculating for here. This number represents only one of these sections. Each section represents the same value. That's why 0.25 times 5 gives you 1.25 seconds. So once we hit this point, we end up with 1.25 seconds. Now, full Ohm's law value is relative to what we measure. So if we start down the path here, this is an exercise I'm not going to force you to go through, but I just thought I would put it up so you can kind of see the idea behind it. So here, say for example, we have a 10 amp load, whatever it's going to be. So 10 amps. So what it's saying here is when we look at our units, it has the buildup and decay tables. So you have 0.632. So in the first time constant, when you close the circuit and you apply power, it's going to go from 0 to 63.2% of its total. So 63.2, so 6.32 amps at this point. In the second time constant, which would be, depending on what we calculate, it'll be at 8.64, 8.65, I'm just using numbers here, but 8.65, 9.5, 9.49 round up, 9.81, and 9.93, 9.92, either way. So we have 63%, 86%, 95%, 98%, and 99%. So what's going on here is you got 10 amps times 0.62. So you got 6.32 amps that has been accounted for in the first time constant. So what's remaining here, so you got 10 amps minus the 6.32, so there's 3.6 amps remaining that has to build up in this part here. So now what's going on is that 3.68 amps, 63.2% is what's going to, that's why these numbers are a little funky, but so 3.68 amps times 63.2% gives you 2.32 amps. So 6.32 plus 2.32, now you have 8.64 amps at the second time constant. So that, at this point, has built up to this value. So 10.8 minus that value, there's 1.36 amps remaining to build up. And we're just going to go down that process. So 1.36 amps times 0.632 gives us 0.8859. We add that up, you end up at 9.49 amps, and you got 9.5. what's remaining? 10 minus that gives you 0.51 amps. We take that at 63.2%. 0.322 gives us 9.81. And to finish it off, the 10 amps minus what has accumulated already gives us this remaining. We multiply that by 0.632, we get this value. And we are at 9.93 amps, and we're looking at that. Now, one thing to understand about this is a 10 amp load. Mathematically, you will never reach, well, not but either way, mathematically, this is going to continue on. Because the 0.632, you're always going to be taking the remaining of what's left over and multiplying it by 0.632. So this is relatively, this can keep going, obviously. But for the sake of measurement and for the sake of how it's all applied, we'll just say that at 5 time constants, it reaches its 10 amp value. And that's something to understand about time constants. So just an example here. So if a coil has an inductance, L, 1.5, wire 6 ohms, battery will give it a 3 volt power source. How long will it take to reach the full Ohm's law value? So T equals L over R, with the ratio of L to R. 1.5 to 6 gives us 0.25 time constant. Now again, what we're talking about is this value. That just so happens to be, but we'll find different numbers. But we're always calculating for just one portion of time. So 0.25 seconds equals 1 time constant. Full Ohm's law value is this number multiplied by 5. The current in this circuit is 3 volts to 6 ohms, gives us 0.5 amps, and that's 0.5 amps at 1.25 seconds. So if we use our tables, the buildup at the third time constant, the tables can be found on page 363 for the buildup and page 364 for the decay. So we just apply our values in the table. 0.5 amps, 0.95 times 0.95 because we're at the third time constant. So the decay at the third, I'm just keeping it the same. Let's see if you can notice the relationship here. So 0.475 amps and 0.025 amps. So if we change it up, now what we'll do is we'll just go through, watch what's going to happen here to the time constant as we change the values here. So we have an L of 2.5 henries, and we're going to change the resistance. So battery 12 volts, wire 12 ohms, full Ohm's law value. To our numbers, 0.2083 seconds equals 1 time constant. So 0.2083 seconds again times 5 gives us that value. So 12 volts, 12 ohms gives us 1 amp at the full Ohm's law value. Fourth time constant gives us 0.981. These numbers are pretty simple. And there we go. So now look what happens as we change the wire resistance here. So 2.5 henries, 12 volts, 10 ohms. 2.5 to 10 gives us 0.25 seconds. And then the full Ohm's law value, 0.025 times 5 gives us 1.25 seconds. So we have now 12 volts to 10 ohms, and then we have 1.2 amps. So if we look at the previous one here, 12 volts, we have 1 amp. We have less amperage. So, and it took 1.04. Here, we increased the amperage, and the time to reach its full Ohm's law value also went up because we have more amperage that we have to build to. So I just wanted to sort of, and if you keep going with this and you go change this to 8 ohms, those numbers are just going to keep climbing because your amperage is going to keep getting larger. So the buildup at the first time constant, take our amps in the circuit, multiply by in the table, first time constant here, and we get these values, 0.758 and 441. So now if we change the henries, we have 3 henries, 12 volts and 6 ohms. So 3 to 6 gives us 0.5 second, one time constant, full Ohm's law value, 1.5 seconds times 5 gives us 2.5 seconds. 12 volts, 6 ohms, 2 amps. We have third time constant, take that number, multiply it, and again, always double check my numbers. And there we go for those values. Now, if we just change the henries here, so 3.5 henries, so the inductance is larger now, but the resistance is staying the same. We have 0.583, one time constant. Now notice we went from 2.5 to 291. Same current, but we have more inductance. So if we add inductance, it affects how it builds or the amount of time it takes to build. If we have more current, it affects the amount of time it takes to build. So I just wanted to show that relationship there between them. So we got 2 amps for a time constant, apply the numbers, 1.96 and 0.038. So here's one for you. Try it out. Pause the video, plug in the numbers. So we got 4 henries. Now just think about what's going to happen. 12 volt source, 6 ohms, all over R, one time constant. Pause the video, and I'll change it now. So there we go. So we end up with 4 ohms, 0.66, kind of a nasty number here. But here we go, 3.3, 2 amps. Again, it built. We went from 4, 1.26, 0.736. So now, have you noticed? The first time constant buildup is 0.632. The first time constant decay is 0.368, which is 1 minus 0.632. So all the decay values are opposite to the buildup. It loses basically when you apply power, it builds to 63.2. And when you remove power, it loses 63.2, and so on as far as the tables are concerned. So I just wanted to cover that, and that is it for time constants and henries.